Hey guys, hope everybody's doing all right. What we're going to do right now is take a look at the first two items on this list of intermolecular or interparticulate forces. The last two things on the list we'll talk about a little bit later. Molecular substances and covalent bonding and the intermolecular forces involved there will be some review from honors, and the macromolecular substance or covalent network will be relatively new, but it's not a huge bit of information on that. So we'll focus more on ionic today, which is also going to be a review of some stuff that we know. Metallic is a little bit new. We'll talk about alloys towards the end. And then we'll worry about number 3 and 4 at a later point in time and build upon those. So starting with ionic compounds, we know a lot of this already. They're held together by ionic bonds, which is really just the attraction of oppositely charged ions, positive cations and negative anions. So you have your crystal lattice structure like this, where you have your series of positives and negatives attracted to each other. And another way to say Coulombic attraction here, like what really is Coulombic attraction, is the attraction of opposite charges, which is just electrostatic attraction. So remember, we talked about in Unit 1, we have two factors that determine how strong the ionic bonding really is. You could have multiple different ionic compounds, but some will have a higher melting point or lattice energy than others. And that has to do with the magnitude of charge, primarily, right? And then it also has to do with the size of the ions. So going from there, it's a relatively strong force. It's one of our strongest intermolecular or interparticulate forces, and we'll have a master list a little bit later when we get through all of them. And additionally here, it's not really a molecule. So I know I say that sometimes, but it's really just a network of positives and negatives. Okay, so we really call it a formula unit. Like we can break down ionic compounds into formula units. But they're not really molecules. Okay, think of a molecule as in like water. Okay, H2O. You have one water molecule. It's really separate from the other water molecules. The only way one water molecule is like connected to another one is through hydrogen bonding, which is an intermolecular force. There's no real like bond between one water molecule and another one. Here you just have this electrostatic attraction. There's really no like breaking point in this, like here's a negative, a positive, negative, positive, negative, positive. They just keep going. It's not like you can say, well, here's a molecule, right? Because it's just not like that. So just a little bit of vocab for you there. You really break down ionic compounds into formula units, and there's some other more specific information about those that we don't get into in this course. So additionally, some properties for ionic compounds. We've been through this a couple times here, either in this course or in honors, I think. So they have high melting points, solid at room temperature, brittle. They do not conduct electricity as a solid. Okay, so that's important. What I tend to do here is when I teach this, I tell students to think of the most common ionic compound you could think of, which is table salt. And then think about the properties of table salt. All right, and then you really can't get these wrong. So if you think of the properties of table salt, and I said, well, what's the melting point of table salt? You'd probably say, well, a big number, right? It's a high melting point. You can't just melt salt very easily. Like you can melt sugar pretty easily, but you can't melt salt very easily at all. So high melting point for those. Really every ionic compound we could come into contact with is a solid at room temperature, right? So that kind of takes care of itself there too, right? If you think of table salt, it's a solid at room temperature, we're good to go. Brittle, you can crush it easily. We'll look at that. There's a little visual in one of the activities we do a little bit later on, where you can see how that actually works in terms of why is an ionic compound brittle. So when you whack it with a hammer or whatever, for a split second in time there, the positive ions will and negative ions, they shift, right? So instead of having positive, negative, and then lining up with each other, being attracted that way, you'll end up with two positive ions next to each other, two negative ions next to each other, and then the like charges repel and pull them away or push them away. Okay, so they're brittle. Like I said, don't conduct electricity as a solid, but they do conduct electricity when melted or when dissolved in solution. So I know I did a demo in honors where I had salt water with a little conductivity probe, and it conducted electricity very well. So students tend to remember that, and they'll think of salt water, and they'll say, yeah, that conducts electricity, no problem. They don't really think of if you actually have molten, melted salt, will that conduct? And it will. That allows the ions to move, right? And that's how we're going to get that electricity being conducted. When the ionic compounds are solids, you really don't have that free movement, right? So it's going to be hard for it to conduct electricity. When it's melted or dissolved in solution, we have that. So obviously, because of that, they're soluble in water. Remember our solubility rule, like dissolves like, which we're going to try to stay away from in terms of how we explain solubility. We'll get to that later on in this unit. It all comes down to the force of attraction. So ions are extremely polar. We don't really call them polar. They're like megapolar. And water is also polar. And because you have some attraction between those molecules, the polar water is being attracted to the ultrapolar ions, right? It pulls them away from the crystal lattice, and you get those ions floating around in water, which makes your ionic compound solution. Salt water, whatever, any double replacement lab we've ever done has ionic compounds dissolved in water, and they're solutions, right? So those are some general properties that we probably knew about already. So moving on to metallic bonding, we want to focus on the valence electrons for this. So here I have some random metal. So you have your nucleus here, that positive charge. Then you have all these electrons on the outside. Not all metals are, but a lot of metals are relatively big. A lot of them are, a big chunk of them is in that transition metal section where you have that D block. So the valence electrons are going to be important in terms of what they do and how they give metallic bonding the properties that it has. So metallic bonding obviously holds atoms together in a metal. So if I said what's the primary bonding in zinc, it's metallic bonding, or in copper, it's metallic bonding. And how I explain that is the metal atoms have a weak attraction for valence electrons. So a lot of the metals are bigger, right? So the valence electrons are a little bit further away from the nucleus. And they have a little bit of a weaker attraction. That's important because it allows them to kind of move around a little bit. So the loosely held electrons are free to move among the positive cores. So if you could try to picture some of these yellow electrons here, these negative charges, kind of bopping around to all the positive nuclei here. That's really what the electrons, those valence electrons, are doing in metallic bonding. And I have a little bit of a visual and a little video clip on the next slide, I think, to show you. But they're loosely shared. Okay, so this electron might bop over here, this one might bop here or there. So they're a little bit more of a free movement of electrons. And that gives metal some of their characteristic properties. Here's a better visual, right? And there's going to be a video clip in a second you'll watch. But you can see how the electrons are kind of bopping around all the different nuclei here. And it creates something called a sea of electrons. So I may have mentioned this in class earlier. This is important here. These are delocalized electrons. Localized means kind of in one place. Think of local, right? One place, kind of stay in that general area. Delocalized means they're more free to move around, and like I said, go to the different nuclei around here. So any sort of textbook or clip you watch will mention this delocalized electron movement as a sea of electrons. Okay, so you try to visualize that there. By sharing these electrons, the atoms form a bond that holds them all together. So that sea of electrons, that bopping around here to all the different nuclei, creates some relatively strong attraction between all of these atoms. And it's one of our stronger forces of attraction that we're going to look at in this unit. So we're going to watch a clip here real quick on metallic bonding, get a little bit of a better visual, and then we'll move on.
The behavior of aluminum is governed by a different kind of force. Aluminum is a metal with an electron cloud of 13 electrons per atom. 3 of these electrons are available for bonding. You can think of each atom as a positive aluminum ion with 3 mobile valence electrons. Aluminum's properties are best explained by a model consisting of a crystalline array of positive ions engulfed in a sea of valence electrons. The particles in aluminum are atoms, but the forces that bind them together are forces of attraction between mobile electrons and fixed positive ions. Aluminum's 3 valence electrons per atom make these forces pretty strong. As energy is added to condensed aluminum, most of it is absorbed by increased ion vibration and electron motion. At room temperature, however, vibrations are not strong enough to break down the metal's crystal structure. This is why at room temperature, aluminum is a solid. In summary, the state in which a substance exists at room temperature depends upon the strength of the attraction between its particles. Can you use this principle to explain why almost all liquids and gases at room temperature are molecular substances?
Okay, properties of metallic bonds. This is a review of honors. So we have, like I said, a relatively strong force, strong sense of attraction, fairly high melting point. Metals are generally solids at room temperature. The only one that's not is mercury. Mercury is a liquid at room temperature. That's the only metal that's a liquid at room temperature. All the rest are solids. They conduct electricity due to that sea of electrons. They're malleable, sometimes even soft. Lead is very easy to bend. Sheets of lead I have in school are very easy to cut through that I use for a single replacement lab. You may remember that from honors. Another term here is ductile. Ductile is being able to be formed into a wire. Malleable is hammered into a thin sheet or bendable. That's really about it. Oh, high luster. Okay, some other properties of metals. But if we're looking solely at the metallic bonding properties here, this is what we have. So moving on from metals, is something called an alloy. An alloy is a homogeneous mixture where at least one of the components is a metal. Most of the time it's two metals. You're going to recognize one of the alloys that I may talk about here because we used it in a lab earlier in the course. We did the percent copper and brass lab, right, where we had that Beer's law curve that we made, and we took a look at the brass sample. We dissolved it in nitric acid. We figured out what the percent copper was in that. So that is an alloy. Brass is an alloy. And different alloys can give metals, like when you combine these metals to make alloys, they could enhance the properties. So if you take a metal that's relatively strong and you make an alloy with it, you might even be able to make it stronger. Or you might be able to make an alloy that's really, really lightweight but very strong. Okay, so alloys are very useful, and you probably recognize some of them. So you have some rims on obviously a car, tire, or wheel right here. So that's an example of an alloy. Some brass fittings. You might have brass doorknobs or hinges in your house. Stainless steel appliances. That's an alloy. All right, or silverware. Jewelry as well is some of the cheaper like costume jewelry could be in the alloy form. So it's a homogeneous mixture, and you have at least one metal. What we're going to do is look at some different types of alloys here in this little clip. And then we're going to do a little POGL activity on the two different types of alloys. Pretty straightforward, pretty easy stuff. But all alloys typically retain a sea of mobile electrons and also remain conductors of electricity. In some cases, the alloy formation alters the chemistry of the surface. And we'll talk about this a little bit actually in the unit 7 at the end of the course in electrochemistry. Some alloys form this oxide layer over the top of your metal, which is actually a protective coating or protective layer. So that's really cool too. So it actually protects the underlying surface from corrosion or just some natural wear and tear. Okay, let's check out this alloy clip and then we'll wrap it up.
We see how different metals bond together to form alloys, which still retain the metallic properties of the starting metals, but are usually stronger. Metal atoms are typified by having only a few electrons in their outer shells. This means that even when they bond, there's always room in this valence shell for more electrons. Each metal atom can bond with up to 12 others in a close packed lattice. Look at the red atom. It is surrounded by 6 in its plane, and 3 on top and 3 underneath. Less compact crystal structures are possible too. For example, this arrangement where each atom is bonded to 8 others. Because there are still not enough electrons to complete the outer shell of any of the atoms, the electrons can move easily from one atom to another, making metals good conductors of both electricity and heat. And because the electrons are not localized in fixed bonds, the atoms can slide past each other, making them ductile, allowing the metal to change shape. It also means that when you try to react metals together, the atoms normally just mix into the lattice, forming metallic bonds with each other, and with no fixed proportions and randomly distributed. These structures are called alloys. Contrast this with compounds between metals and non-metals, or between non-metallic elements, where the proportions of each element is fixed. The oldest example of an alloy, perhaps, is the way bronze took over from copper in the early human communities of Europe around 6,000 years ago. During the late Stone Age, axes began to be made of pure copper, but they were fairly soft. When small amounts of tin were added to make bronze, you got an axe which was twice as hard and worked well. The Bronze Age had arrived. The atoms in a metal lattice are held by non-directional bonds, a sort of sea of loose electrons, as we said, allowing the atoms to slide past each other, still touching, making metals relatively easy to melt and bend, but hard to vaporize. When metals change shape, atoms actually slip over each other like this. However, this process does not happen all at once, but bit by bit, rather like trying to move a carpet by putting a ruck in it. Here is the way it happens in a metal. You see the slip moving easily one atom at a time where there's a dislocation in the lattice. It is this easy movement of atoms in the crystal lattice that makes most pure metals soft. Now put a smaller or bigger atom into the lattice, and this easy movement of the dislocation is blocked. See the way the bigger atom stabilizes the dislocation, which gets no further unless you put greater force, meaning that it's harder to bend the alloy. To finish, let's look at some well-known alloys. Bronze, 3/4 copper, quarter tin, for sculptures, boat hardware, screws and grill work. Brass, 70% copper, 30% zinc, musical instruments, coins, door knockers. Carbon steel, 99% iron and up to 1% carbon for building construction, tools, car bodies, machinery, rails, etc. Stainless steel, iron with about 18% chromium and 8% nickel, used for tableware, cookware, surgical tools and so on. Aluminium alloys for planes contain a few percent of copper or other metals. Amalgam is mercury with silver and other metals once used for dental fillings. Solder, lead and tin for joining electrical wires and components, melts very easily. Gold is usually an alloy containing another metal such as silver for increasing hardness. The number of carats, K, defines how many mass parts of pure gold are found in 24 parts of the alloy.
Okay, so the two main types of alloys are going to be interstitial and substitutional. So this is a good graphic here of the difference between those. The difference between interstitial and substitutional has to do with the size of the metals making up the alloy. Okay, so you can already see in the picture here, you have the one on the left, you have two metal atoms that are relatively large, or I should say relatively the same size, that make up your alloy. And on the right, you have an alloy where you have larger metallic atoms or larger atoms, and you have some smaller ones, interspersed inside there. So a good little image here I have is these pictures of these jars of rocks. So the rocks on the left, those two jars on the left, could be an example of one type of alloy, right? I won't give away, you're going to do that in a minute. One type of alloy where they're about the same size, and you have another picture over here where you have some rocks that are larger, and then you have some sand, which is really small, kind of filling in the gaps like you have in the picture above. So you'll determine which one's interstitial, which one's substitutional in the activity you guys do. You can probably tell maybe by the names already what what these two are, and then they both have different properties that go along with them. So before you go into that, you're going to complete the Your Turn questions at the bottom of your note page. You're going to type your answers into Edpuzzle. You'll get a a score based on just putting forth a clear, educated hypothesis. All right, that should take care of this little intro and some review, some new stuff, and you'll move into the alloys POGL, which will take a couple minutes, and that'll give you more of an in-depth look at the interstitial versus substitutional. All right, thanks guys.